Hi, this is my first video. I'm going to review a paper by John R.P. French from 1956, which is called A Formal Theory of Social Power. In my opinion, it's very instructive in terms of understanding what later opinion dynamics models are doing. And the model that underlies this theory is not an agent-based model, but it's very useful to understand agent-based models that try to model this phenomenon. In this case, we model agents with capital letters A, B, C, and so on, and corresponding opinions with small letters accordingly. We are going to use discrete time units, so starting at 0, then 1, 2, 3, and so on. Power will be modeled as a directed graph, and this is rather simplistic. So we just assume that this relation means A has power over B. Power in this case is conceptualized as force fields along a unidimensional axis. And here is how French visualizes this. We have two axes. The x-axis is the opinion, and the y-axis is the strength of the force that an agent can exert. And we have two agents, A and B, that lie somewhere on the opinion axis. And these lines depict the force fields around A and B. So the solid line around A means that this is the force that A can exert on B. And the dashed lines around B are the resistance that B can set against the force that A can exert. So if you take this point, the force that A can exert is higher than the force that B can resist, so B will move in A's direction. But at a certain point, there's going to be an equilibrium. And for simplicity, we will assume that this is at 1/2 times A0 plus B0. So if this is our equilibrium at time t0, B is going to move in A's direction, and we are going to have a new equilibrium at time t1. Generally, we are going to assume that the updated opinion, or the opinion at time unit n, is going to be the arithmetic mean of all input opinions and the agent itself. So in this case, Cn would be equal to 1/3 times An-1 plus Bn-1 plus Cn-1. Again, for simplicity, we are going to assume that this is a proportional relationship. So the force that can be exerted and the discrepancy between opinions are proportional to each other. That means the higher the discrepancy between the agents, the higher the force exerted. This is probably, or certainly, an oversimplification. This does not factor in an effect that at some point B might reject A's opinion completely. So if the opinions become too dissimilar, B will completely reject A's opinion. Additionally, this model probably also oversimplifies the force field between the agents because, for example, these force fields could also be curvilinear or they could differ between agents. But a model should only be as complex as it needs to be, and for the purposes of this theory, this is good enough. Let's look at a specific example. On the left, you can see the power structure in a group modeled as a directed graph, and on the right, you can see a table with the agent, its opinion, and later the updated opinions. Let's first look at agents A and D. Both agents have no inputs, so their opinions is going to stay constant. Agent B has one input from A, so the updated opinion is going to be the arithmetic mean of A and B, which is 6 plus 2 divided by 2, so 4. Agent C has two inputs, B and D, so the updated opinion is going to be the arithmetic mean of B, C, and D, so in this case 4. This is repeated in each time unit until eventually the system reaches an equilibrium. I have selected 3 instructive examples from the paper, which represent 3 distinct aspects of opinion dynamics that can be explored with this model: power structure, communication patterns, and leadership. Let's start with power structures. As stated before, power structures are modeled with a simple directed graph, and what we want to look at specifically is the level of connectedness in the graph. And the simplest case regarding this aspect is the completely connected graph. Completely connected graphs have directed edges between any pair of nodes in the network. That means you can select any 2 nodes and there will be an edge from the first to the second node and vice versa. The lower next level of connectedness is the strongly connected directed graph. In this case, the following constraint applies. If you select any two nodes I and j from the graph, there exists a path from I to j and from j to I. In this case, for instance, there's a path from D to A, and there's also a path from A to D. And this is true for all nodes in the network, so you can basically select any two nodes and this will apply. Breaking down the constraints even more, we arrive at unilaterally connected graphs. Here, if you select any two nodes I and j from the network, there is a path from I to j or from j to I. So if you take, for instance, A and D, you can see that there is a path between them, in this case from A to D. If you select C and D, there is a path from C to D, and you could show that for any two nodes from the graph. One level further, we are at weakly connected digraphs. Here, the only constraint is that the graph has only one component and does not break down into several components. Notice, however, that there might be pairs of nodes that have no path between them. Here, you could show this for A and D. And finally, the disconnected graph is a graph that breaks down into at least two distinct components. There's not much more to say about this kind of graph because within each of the components, the definitions from before could apply. I will now proceed to show the outcomes regarding opinion formations for networks with the aforementioned restrictions. I will not provide the formal proofs of each scenario, but they are not very complicated if you feel compelled to prove them yourself. Let's again first look at the simplest case, the completely connected graph again. You can see that the opinions converge in one time unit. This is not very surprising because all agents are under the power of each other agent, so their updated opinion will be the arithmetic mean of all agents, and hence all agents converge in one time unit. In a cycle, which is a strongly connected graph, opinions do not converge immediately, but do so in infinite time. And again, the converged opinion in the equilibrium will be the arithmetic mean of all input opinions. In a unilaterally connected graph, there is, by definition, always one and only one node which has no input. In this case, you can see in the upper right corner, this is A. All other agents over time converge to A's opinion, while A's opinion does not change. In a weakly connected graph, there may be several nodes with no inputs, so all those nodes will not change their opinion. Here you can see this is the case for A and D. C converges to D's opinion because it has only one input, which is D. And B is going to reach an equilibrium between A's opinion and C's opinion because it has inputs C and A, and as said before, C converges to D's opinion. Consensus here is only possible with very special distributions of input opinions. So we cannot assume that there is going to be a consensus in a situation like this. Here you could see if A and D had the same opinions, then the whole system would converge to one opinion value. But as I said, this is only the case for very special input opinion distributions. For the disconnected group, there is not much to add. It breaks down into several components, and within each of the components, everything mentioned before applies. So B and C converge in one time unit because it's a completely connected graph, and D converges to A's opinion because it's a unilaterally connected graph. Overall, we can see that there is a funneling effect, which is increasingly apparent with increasing connectedness in the graph. So what you could say is that we have now a very basic theory of consensus formation on our hands. Now let's move on. We want to look at communication patterns next. So far, we have assumed that each agent exerts power in each time unit. And in this case, in a three-person or three-agent cycle, this would yield an equilibrium at 1/3 times A0 plus B0 plus C0. This is what we have seen before. Now let's assume that the communication pattern changes and A communicates in the first time unit, then B and C in the second, then A in the third, and so on. Now, intuitively, you could say that this system converges at the arithmetic mean of the input opinions again. At least that would be a reasonable assumption. However, if you play this out, you reach an equilibrium at 1/5 times 2A0 plus B0 plus 2C0, which is substantially different from the arithmetic mean of the input opinions. So you can see that communication patterns do play a role in opinion formation. In this case, you could argue for something like a primacy effect. Lastly, let's look at leadership. For this phenomenon, it's easiest to consider a unilaterally connected graph. There is always a clear candidate for a leader because there is one and only one agent with no input. So in this case, you can see it's A. A has no input, and there is also no second node with no input. This system can be modeled via difference equations. So let's start with A. A's opinion, as stated before, will not change. So at time n, it will be the same as at time n minus 1. B has one input from A, so the updated opinion is going to be the arithmetic mean of A and B from one time unit before, and the same applies to C. And D has two inputs from B and C, so the updated opinion will be the arithmetic mean of B, C, and D from one time unit before. If we write this down as a matrix, we get something akin to a leadership matrix, and we call this matrix capital M. Each cell denotes how much influence each agent has had on each other agent. And if you take the column sums, you get the influence each agent has had in the entire system. Now what's cool about this is that if you raise M by the power of n, you get the influence each agent has had on each other agent after n time units. So M squared is the matrix of influences after 2 time units, M cubed after 3, and so on. If you look at the column sums again, you can see that A's influence increases with each time unit while the others decrease. After an infinite number of steps, all opinions will have converged to A's opinion, and A's influence will be 4 while all other influences will be 0. So what are we left with after reading this paper? It's an early attempt at a bridge between psychology and sociology. There has been a lot of research since trying to gauge the effects of individual dispositions on a group level. More importantly, though, this theory is the very basis of many later inquiries into opinion dynamics. There are far more sophisticated theories out there today, especially some using agent-based modeling, but I found this one to be very instructive in terms of understanding the very basics of the field, and I hope that what I covered in this video will be helpful in understanding more sophisticated models.